Morning. Myself Prabha J, working as an assistant professor in EC department at SNS College of Technology. In this lecture video, I am going to discuss about the topic name is Butterworth filter design from Unit 2, that is IAR filter. From subject name is DSP, Digital Signal Processing. Let me discuss. Design of low pass digital Butterworth filter. The popular methods of designing IAR filter, which means IAR digital filter, involves the design of equivalent analog filter and then converting the analog filter into digital filter. Hence, to design a Butterworth IAR filter, um, first an analog Butterworth filter transfer function is determined using the given specification. Then the analog filter transfer function is converted to a digital filter transfer function by using either impulse invariance method transformation or bilinear transformation technique. The analog Butterworth filter is designed by approximating the ideal analog filter frequency response, which is h of j omega using an error function. The error function is selected such that the magnitude is maximally flat in the pass band and monotonically decreasing in the stop band. The Butterworth filters are all pole designs. At the cutoff frequency omega c, the magnitude of normalized Butterworth filter is 1 divided by root 2. Hence, the decibel magnitude at the cutoff frequency will be 3 decibel less than the maximum value. The filter order n completely specifies the filter. The magnitude is maximally flat in the origin. The magnitude is also, which is monotonically decreasing function of omega. The magnitude response approaches is ideal response as the value of n increases. Also, the transfer function of analog Butterworth filter, for a stable and causal filter, the poles should lie on the left half of S plane. Hence, the digital filter transfer function is formed by choosing the n number of left half poles. When n is even, all the poles are complex and exist as conjugate pair. When n is odd, one of the poles is real and all other poles are complex and exist as conjugate pair. Therefore, the transfer function of Butterworth filter will be a product of second order factors. And the normalized Butterworth low pass filter transfer function, capital N is the order of the filter, and h of s suffix n is the normalized Butterworth low pass filter. Here you can see the formula for when n capital N is even, h of sn equal to k equal to 1 to n divided by 2 divided by 1 divided by s n square plus bk sn plus 1. Also, you can see the formula for n is odd. Unnormalized Butterworth low pass filter transfer function, normalized is undone by replacing Sn by S divided by omega c, where omega c is the 3 decibel cutoff frequency. This gives the actual unnormalized filter. Here you can see when n is even, h of s equal to k equal to 1 to n by 2, 1 divided by Sn square plus bk Sn plus 1, where Sn equal to S divided by omega c. Normalized is undone by replacing Sn by S divided by omega c. Same process as previous slide, but formula is shown by odd n, which is h of s equal to 1 divided by Sn plus 1, where k equal to 1 to n minus 1 divided by 2, 1 divided by Sn square plus bk Sn plus 1, where Sn equal to S divided by omega c. This is the table for Butterworth low pass filter normalized transfer function. When n equal to 1 to 6, the transfer function shown this diagram. This slide shows the magnitude response of an analog filter uh, maximally flat at DC, which means 0 hertz and no ripples in passband frequency. Here you can see the order of the Butterworth filter formula for the order of the Butterworth filter. N1 equal to 1 by 1 divided by 2 for numerator log of 1 divided by as square minus 1 divided by log of 1 divided by as ap square minus 1 divided by denominator term log of omega s divided by omega b. This is the formula for order of the Butterworth filter. And this is the another formula which means in terms of decibel, the formula for the order of the Butterworth filter. And mention two conversion method. Here you can see the analog to digital conversion by using two methods. First one is bilinear transformation technique and second one is impulse invariance method technique. Bilinear transformation method techniques, passband frequency is cutoff frequency is passband frequency 2 divided by t tan of omega p divided by 2 and stop band frequency omega s equal to 2 divided by 2 t tan of omega s divided by 2. Similarly, impulse invariance method, passband frequency omega p equal to omega p divided by 2, analog frequency represented by omega suffix p equal to digital frequency passband frequency divided by t, and stop band frequency omega s equal to omega analog frequency omega digital frequency omega s divided by t. This is the formula for impulse invariant method technique. Here you can see the cutoff frequency of low pass Butterworth filter, and A suffix P and A suffix S passband attenuation is represented by AP, stop band attenuation is represented as AS, and omega P omega S is passband digital frequency which is represented as omega P, and stop band digital frequency which is represented as omega S. And cutoff frequency omega c equal to stop band frequency omega s divided by 1 divided by a stop band attenuation as whole square minus 1 whole power 1 divided by 2 power capital N. N is nothing but the order of the filter. Similarly, or either we can use passband frequency for the cutoff frequency formula, omega c equal to omega p divided by 1 divided by ap square minus 1 whole power 1 divided by 2n. This is the formula for the cutoff frequency of low pass Butterworth filter. And in decibel, in terms of decibel, the cutoff frequency omega c the specification alpha p in terms of decibel, passband attenuation represented as alpha p, stop band attenuation represented as alpha s, and omega p is nothing but the digital frequency, passband digital frequency, omega s is nothing but the stop band digital frequency, and cutoff frequency when we are using stop band frequency, when we are using passband frequency, two formula here. Here you can use two formula, either omega stop band frequency or passband frequency. And this is the terms you should know about these terms before the design. Omega p is nothing but the passband digital frequency, and omega s is nothing but the stop band digital frequency, and APAS is nothing but the gain at passband frequency, which means attenuation at passband, attenuation at stop band, and already you know the time period t equal to 1 divided by inversely proportional to the frequency, and also fs is nothing but the sampling frequency, omega p omega s is the analog frequency, passband analog frequency omega p, omega s is the stop band analog frequency. This is the design procedure for low pass digital whatever the AR filter. For analog to digital, we have to use two methods, either bilinear transformation technique or impulse invariance transformation. For bilinear transformation technique, you have to use passband cutoff frequency, passband frequency omega p equal to 2 divided by t omega tan omega p divided by 2 omega s equal to 2 divided by t tan of omega s divided by 2. Here given is omega p analog sorry digital omega, and given is stop band and pass band digital omega, which means digital frequency. And impulse invariance method formula is omega p equal to omega p divided by t. Analog frequency equal to digital frequency divided by t. Passband frequency, analog stop band frequency equal to digital stop band frequency divided by t. Next, have to calculate the order of the filter. For order of the filter, we should know about the stop band attenuation value, pass band attenuation value, and stop band frequency and pass band frequency value. Then only we can calculate the order of the filter. Next is normalized transfer function of the analog low pass filter. For n, when n is even, this is the formula h of sn equal to k equal to 1 to n by 2 divided by s square n square plus bk sn plus 1. When n is odd, this is the formula. You can see h of sn equal to transfer function equal to 1 divided by sn plus 1 k equal to 1 to n minus 1 divided by 2 divided by 1 divided by sn square plus bk sn plus 1. And next step we have to calculate the analog cutoff frequency. Cutoff frequency, this is the formula for the cutoff frequency. Omega c equal to stop band frequency divided by 1 minus stop band attenuation minus 1 whole divided by 1 divided by n. Next step is how to calculate unnormalized analog transfer function, which is h of s, is obtained by replacing sn by s divided by omega c in the normalized transfer function of the low pass filter function. When n is even, we have one formula, and n is odd, we have another formula. N is odd, we have a formula. This is the formula for n is odd. Next is how to calculate transfer function of the digital filter, which is h of z, and then by using either bilinear transformation technique or else impulse invariance method technique, and then how to realize the digital filter using suitable structure. And last step, final step is to verify the design by sketching the frequency response, which is h of e power j omega equal to h of z, where z equal to e power j omega. Okay, design procedure, first step of the design procedure, you have to calculate the frequency response, which is a digital frequency response. Then have to calculate order of the filter, and have to calculate unnormalized low pass filter transfer function. After that, have to calculate the transfer function from analog filter to digital filter using a bilinear transformation technique or else impulse invariance method technique, and realize the transfer function using suitable realization structure. After that, sketching the frequency response. And this is the assessment for this lecture. First is compare impulse invariant and bilinear transformation technique, and second question is what is Butterworth approximation, how will choose the order n for a Butterworth filter, and list the properties of Butterworth filter. Analog filter transformation is converted to digital filter transfer function by using either dash and dash, and define sampling time. This is the assessment for this lecture. If you have any doubt, you can ask me through the comment. We will meet in next video. Thank you.